coming in online, Alon and Horin, and the title is Privacy-Preserving Collaborative Filtering by Distributed Mediation.
Okay, so hello, my name is Alon and Horin. I've just finished my studies towards a master's degree in computer science at the Open University of Israel. My supervisor was Professor Tamir Tassa, and in this talk I will describe our joint research on privacy-preserving collaborative filtering by distributed mediation. Recommender systems provide a framework for vendors to offer their users items that appear to be most suitable for them. Collaborative filtering, CF, is one of the main methods that recommender systems use to assist users in finding their most suitable products. Such predictions are made based on past activity of the users. To enable more precise predictions, it is desired to enlarge a training dataset. To that end, several vendors may collaborate and conjoin the user item rating data that they hold. However, such collaboration may jeopardize the privacy of users. It is also reasonable to assume that the vendors may wish to refrain from sharing information of commercial value with others. For those reasons, we would like to perform the CF computations based on the distributed data in a privacy-preserving manner. Shmueli and Tassa introduced the notion of mediation into privacy-preserving collaborative filtering. They assumed that there exists a mediator to whom the vendor sends the user item rating data under homomorphic encryptions. That mediator performs the CF computations on the encrypted data. And they showed that the mediated setting has many advantages, such as reducing the need of the vendors to communicate between themselves, as well as a reduction of the overall communication cost. We take the idea of mediation one step further by assuming multiple independent mediators. Distributing the mediator brings about significant advantages. With the distributed mediator, we can replace expensive homomorphic encryption with lightweight secret sharing schemes, and by thus reduce runtimes dramatically. And while the single mediator scheme is vulnerable to collusion between the mediator and a vendor, the distributed mediator scheme is collusion resistant. So what are secret sharing schemes? Those are methods that enable to distribute a secret among a set of participants. Each participant receives a share, which is a random value that is related to that secret. In Shamir's D prime out of D scheme, every subset of D prime shares can be used to fully recover the secret, while any subset of less than D prime shares reveals zero information on the secret. Each of the vendors will distribute to the D mediators D prime out of D shares in each entry in the user item matrix that he possesses. In our method, D prime is set to equal the integer part of D plus 1 over 2. Such a setting implies that in order to recover the secret, more than half of the mediators would need to collaborate. We assume that the mediators have an honest majority. That means that if there exist corrupted mediators who will try to collude and recover the secret data, their number is less than that of the honest ones. Hence, with our settings of the threshold D prime, user item data will remain hidden from all mediators. Yet, they can still perform the CF computations on the shares that they hold. Our system consists of two phases. In the offline phase, the vendors share their data among the mediators, and then the mediators compute the metrics of item-to-item similarity scores. Then, in the online phase, the vendors submit queries to the mediators regarding predicted rating or ranking, and the mediators reply to them. Now, let's talk a little about the distribution of the global user item rating matrix, among the vendors. Previous art assumed horizontal, vertical, or hybrid distribution scenarios. In all those scenarios, each entry in the matrix is owned by just one vendor. We, however, assume a general distribution scenario where each vendor owns a submatrix and the submatrices may overlap. Namely, a user who wishes to purchase some item has a choice between competing vendors. The goal of the offline phase is to deliver to the mediators the user item data in a protected manner, and to compute the matrix of similarity scores between items. In the first step, each vendor shares every entry in his submetrics with the D mediators in a D prime out of D secret sharing scheme. Then, the mediators accumulate those shares so that at the end, each one of them has D prime out of D shares in each entry in the global user item rating matrix. Subsequently, they engage in a secure protocol to compute the similarity scores for each pair of item from the shares that they had just received. How is that computation done? Well, the prediction regarding the rating a user would give to some item is based on similarities between that item and other items. Those similarities are determined using the cosine similarity score. The computation of that score requires computing 3 scalar products between n-dimensional vectors. However, while the mediators possesses shares in those vectors, they do not know the actual vectors. So here's the challenge. How to compute scalar products between unknown vectors? Our protocol solves that conundrum. See our paper for more details. One query that the vendor may wish to submit is the following. In the online phase is the following. UN is a user in my clientele, and BM is an item for my store. Please evaluate for me the predicted rating that UN would give to BM. The mediators go about and compute that prediction based on similarity scores and shared user item ratings that they had just received in the offline phase. Another query that the vendor may submit is the following. UN is a user in my clientele. Please find what are, say, the 5 items from my store that would most appeal to him. Such a query starts another exchange of messages between the vendor and the mediators that ends with the requested items sent to the vendor, while the mediators do not learn any sensitive information in the process. Please see our paper for the details of the processing of those 2 queries. Our protocol, like the single-mediated protocols of Shmueli and Tassa, issue exactly the same outputs as the underlying non-privacy-preserving CF algorithm. Namely, the cryptography shield does not have any effect on the CF itself, but it does have its toll in terms of runtime. We ran extensive experiments with both the distributed and the single-mediated protocols on several datasets to illustrate the viability of our protocols and the overwhelming advantages that they offer, not only in terms of security, that is being collusion resistant, but also in terms of runtime. Let us present the timing result as computed on the Movulance 20 million dataset. The dimension of which number of users n and number of items m are shown in the first table. The second table shows the runtime for a mediator and for a vendor in the offline phase. The first 2 columns show the runtimes of our protocol as function of D, the number of mediators. The next 2 columns shows the runtime of the single-mediated protocol in the 2 settings of the homomorphic encryption key length, 512 and 1024 bits. In that protocol, all of the computational overload is in the vendor side. As can be seen, the differences are staggering. Our protocol is roughly 3 orders of magnitude more efficient. The third table shows runtime for finding the most recommended items. Here too, the differences are very significant. By the way, more than 99% of the shown runtimes for our protocol are spent in computing scalar products. Such computations are executed also in the non-private algorithm. Hence, the price of privacy in our mediated protocol is very small. In the future, we intend to examine the applicability of distributed mediation to other CF algorithms, such as matrix factorization-based algorithm, and compare their performances to that of existing privacy-preserving implementation of those algorithms. That's it. Thank you. Please check the paper for more details.
Thank you. Thank you for the presentation. Please walk to the microphone if you have questions on site, or use the online version to type in your questions. May I start with one question? Privacy is in some domains more important than in others, or more prevalent than in others. And you used like the Movulance dataset. While the approach is more or less generic, can you think about applying it to other domains that are where privacy is like really highly sensitive data is used. Have you thought about that? How
I
typical
didn't really
it is?
understand the question. What do you mean using the movie-lens 20 million?
No, using a different domain, for instance, with health-related data, medical data, where it's highly sensitive data.
Yeah, so our protocols is designed to give recommendations based on ratings that are numeric. So our protocols can be changed to answer recommendation for every data set, not only movies, if it's numeric. So if it's between 1 to like 10.
Okay, thank you. Refreshing the thing. Yeah, you already said what could be next steps to follow on. There's a question coming, so I don't have to move forward. Hi, White Vancouver says, hi, thanks for the interesting talk. Can you give us some real-world examples of vendors cooperating together in the way you described in your talk?
Yes. So, for example, if Amazon and eBay want to collaborate and use each other in order to give more precise predictions for their clients, they can collaborate in a secure manner, as I describe in our protocols, and give better predictions to their users.
Okay, thank you. Another question coming in. Do you have performance improvements in terms of RMSE by using different vendor data versus using own data?
Can you repeat that, please?
Do you have performance improvements in terms of RMSE by using different vendor data versus using own data?
Our protocol, we compared to the single-mediated that Tassa and Shmueli showed in, I think, one of the RecSys before this year. And we showed dramatic, and actually we make the improvement of runtimes be like much, it was very dramatic, the improvement of runtimes, and we make the protocols usable in the industry.
Okay, thanks a lot. More questions are flowing in, so please go online, and I think that's fruitful for further discussion. Let's thank our speaker again.
Thank you.